Okay, let's dive right into this. Today, we're taking a journey into the incredibly elegant and honestly kind of mind-bending world of differential geometry. In this explainer, we're going to explore the mathematical architecture of the space all around us. We're talking the whole shebang, from the simplest curves to complex, paradoxical surfaces. We'll be looking specifically at tangents, derivatives, normals, and orientability. If you've ever wondered how mathematicians actually define the shape of space without just eyeballing it, well, this is exactly how it's done.
But before we get deep into the calculus, I want to start with a question to really frame our thinking. Does every surface actually have an inside and an outside? It sounds like a total trick question, right? In our day-to-day lives, obviously a sphere has an inside and an outside, a cardboard box has an inside and an outside. Our intuition just screams that spatial reality is strictly divided into these two domains. But mathematically speaking, is that always true? Keep that philosophical hook in the back of your mind as we build our dimensional toolkit from the ground up.
Section 1. 1D space, the geometry of curves. So to truly understand complex surfaces, we first need to master the building blocks. And that means starting with the simple one-dimensional curve. Let's look at the tangent vector. When we look at a curve mathematically, we parameterize it, meaning we imagine a point moving along it over time. The tangent vector is simply the first derivative of that parameterized curve at one specific moment. In the language of calculus, if your curve represents position, that first derivative is your velocity. It tells you the exact, precise direction the curve is heading at that very instant. Think of it like this. If you were driving along this curving path and suddenly let go of the steering wheel, the tangent vector is the straight path your car would take. Now, what's really interesting here is how we physically visualize this mathematical limit. Imagine picking a point on a curve. Then, pick a second point nearby and draw a straight line, a secant chord connecting them. Now slide that second point closer and closer to the first. As the distance between the 2 points shrinks to absolute zero, the length of that chord shrinks to zero too. But its direction, it perfectly aligns with the tangent line. It's this beautiful kinesthetic analogy. The tangent vector perfectly captures the instantaneous direction of a 1D path. But you know, a curve isn't just a straight line, it bends. And that brings us to curvature. If the first derivative gives us the straight tangent line, curvature is the exact measurement of how much our path deviates from that straight line as we move forward. Mathematically, we find this via the second derivative, or acceleration. For a curve traveling at a constant speed, its acceleration vector is entirely dedicated to changing direction. The magnitude of that deviation tells us exactly how sharply our curve is bending away from its tangent. Section 2. 2D surfaces, moving to 3 dimensions. We know how to find the direction of a 1D line, but how do you find the direction of an entire 2D surface? Let's see how this builds from 1 dimension to 2. We've nailed down curves, right? While a 1D curve has just one single forward tangent line at any specific point, a 2D surface changes the game entirely. If you stand on a curved surface, like say a grassy hill, you can walk forward, backward, left, right, or literally any angle in between. Because you have 2 degrees of freedom, a surface possesses an infinite number of tangent lines passing through that single point. And when you combine all those infinite 1D tangent lines together, they fan out to form a flat 2D sheet. This flat sheet is formally defined as the tangent space. It's the set of all possible tangent vectors to a surface at a specific point. Visually, imagine taking a completely flat, rigid piece of glass and resting it perfectly on top of a curved sphere. That glass pane kisses the surface of the sphere at exactly one mathematical point. In differential geometry, we study complex curving surfaces by looking at these flat, understandable tangent spaces at every single point. Section 3. Direction and normals. Finding up. This brings us to a really fascinating question. Once we have a flat tangent plane kissing our surface, how do we mathematically define which way is up or down? So the crucial point here is the standard unit normal. To find up, we need a vector that is completely perpendicular to our entire flat tangent plane. This normal vector acts like a mathematical flagpole sticking straight out of the surface. It indicates what we call the positive side. If we have a surface grid parameterized by, say, u and v,
We can find this mathematically by taking the cross product of the tangent vectors in the u and v directions. The cross product essentially takes those two vectors resting flat on the plane and calculates the unique third arrow that shoots perfectly straight up, perpendicular to both of them.
I absolutely love this specific quote from our differential geometry source text. A choice of unit normal enables us to distinguish the two sides of the tangent plane. Think about it for a second. A flat plane divides 3D space into two halves. By choosing a normal vector, we're making a mathematical choice about which half is the positive side. Imagine holding a right-handed screw completely perpendicular to the surface. If you rotate it counterclockwise, it advances outward, right in the direction of the normal vector. That right-hand rule gives us a really concrete physical anchor for positive rotation and definitively separates the inside from the outside. And that establishes the concept of orientability. Orientability is simply a property of a surface where you can make a consistent, smooth choice of this unit normal everywhere on the shape. Basically, it means the surface fundamentally behaves exactly as expected. You could paint the outside blue and the inside red, and never the two shall meet. If you slide your mathematical flagpole all the way around an orientable surface, it will never suddenly flip upside down and contradict itself. Section 4. The paradox. Breaking orientation. Because, as you might have guessed, not all surfaces in differential geometry play nicely by these rules. Up until now, everything has been perfectly intuitive. But prepare to break orientability. And this brilliantly illustrates the grand climax of this whole concept. Look at the contrast. A familiar standard sphere is fully orientable. It has a distinct inside, where all normal vectors point toward the center, and a distinct outside where they all point out into space. But compare that to the paradoxical Mobius band. It is totally non-orientable. Because of its bizarre geometric twist, if you try to define a normal vector, it will eventually mathematically flip. It entirely destroys the concept of having a distinct inside and outside. Let me walk you through exactly how this absurd reality happens. Take this mind-bending journey with me. Step 1. Start a normal vector, or flagpole, pointing straight up from a point on the Mobius band. Step 2. Begin sliding that flagpole along the surface, smoothly following the path of the band. Because the Mobius band has a half-turn built right into its geometry, your flagpole naturally starts tilting. Step 3. By the time you make one full rotation around the band and return to your exact starting mathematical point, your flagpole is now pointing completely down. It's totally wild. The limit approaching from one direction gives a normal of 1, 0, 0, while approaching from the other gives -1, 0, 0. The vector literally directly contradicts itself. Mathematically speaking, it only has one side. Which brings us to our final thought. We started with simple 1D curves, built up to 2D surfaces, and anchored them with tangent planes and normal vectors. But the Mobius band shows us that our rigid, everyday rules of inside and outside can be completely shattered by a simple geometric twist. So I'll leave you with this. If mathematical geometry allows for surfaces that exist with only one side, what other illusions of space, dimensionality, and curvature are waiting to be uncovered in the deeper realms of differential geometry? Thanks for exploring this with us, and keep questioning the shape of the reality around you.